Hello everyone, my name is Johan Nuñez. Today we are going to talk about our paper titled Structural Design and Sliding Mode Control Approach of a 4 degrees of freedom upper limb exoskeleton for post-stroke rehabilitation. As you can see, we are part of the Advanced Biomechatronic Research and Innovation Laboratory at the Universidad Nacional de Ingeniería in Lima, Peru. Well, to start with this presentation, we are going to introduce a short description of what we are going to talk in the following parts. PNF, proprioceptive neuromuscular facilitation, is an approach to exercise therapy that uses specific movements patterns in diagonal and spiral directions together with specific techniques and that facilitate the increase in strength and muscle function. An important principle of PNF is that after a muscle has contracted maximally, it will then relax maximally. In recent years, different exoskeleton models have been developed to achieve an optimal trajectory tracking. Also, the authors analyzes the mean error and response time for each joint angle, but they didn't reduce the tracking error using the control methods. The methodology opted for this research has been divided in three parts: mechanical design, rehabilitation trajectory, and control design. For mechanical design, we have designed 3 degrees of freedom for the shoulder and 1 degree of freedom for the elbow. As you can see in the right side, we have divided two graphs. The first one is for the degrees of freedom. As you can see, we have a model of a person for this case. On the other hand, you can see how we are planning to do the manufacturing parts. In the bottom, you can see a short description of the boundary condition for the simulation setup and the forces included in this case. And finally, in the last part of this slide, you can see some values. These are an estimation for a global properties of the material. For example, the motor and gearbox has a general mass density of these values.
Okay, now in this presentation we are talking about the rehabilitation trajectory and how we have been record the trajectory. For that we obtained the trajectory by the kinetic for Xbox 360, and now the software was the Breaker Kinetic Pro 1 Pro V1. Uh, for for record that we take four angles, that is Q1, Q2, Q3, and Q4. In this part of the view, in the left, we show us how the software interact between the human and the upper limb and all of the body. And on the right, we have four view. There is front, top, lateral view. In the front view, we correspond the Q1, and top view the Q2, and lateral Q3, and lateral view Q4. For the whole of the angle, we take on the MATLAB software, and we have the for processing, and we take about the four angles. Forget the four angles Q1, Q2, Q3, and Q4. We take the law of sines, and after that we get the Q1, Q2, Q3, and Q4 angles. After that, that angle that is an input for the control performance.
To define the dynamics of the exoskeleton, the reference frame surface attached according to the Hardenberg convention. The equations are based on the Lagrange-Euler method, where Q are the angular positions of each joint and represents the internal forces and torques of the system, and FF represents the viscous friction torque. Then we define the sliding surface from the derivative of the error. We consider as constant lambda, and with Lyapunov, we define the limits of the control law. K is restricted according to this equation. Then we simulate the system in Simulink to verify the operation of the controller on the exoskeleton. For this, we use the data of the angles in each joint obtained with the kinetic camera.
Okay, to continue with results, we have divided this capture into main parts: structural simulation and controlled performance. First, structural simulation results have given us a factor of safety to have a minimum value of 1.3 as shown in the figure. In order to improve and assure a good material selection and mechanical design, it was necessary to check if any contact and joint has an stress over the elastic limit. Analyzing the results, it's clear that the maximum equivalent stress is under the limit for each piece in the assembly. In the right side we have the equations applied by the software, and in the bottom we can see three main graphs. The first one is equivalent stress according to von Mises criteria, and the second is the contacts and joint setup. We have the configuration for every part. Finally, the factor of safety, we can see a minimum value of 1.3 in the second link for between the first and the second module.
The values of the control resource K for each joint depend on the components of the inertial matrix of each joint, lambda and phi, from the sliding surface, and n from the viscous torque. Then, as can be seen in these figures, the simulated robot follows the trajectory with a low error, and the introduction of a load hardly affects its operation. For torque values, a maximum value of 20 Newton per meter is presented. There are more oscillations in torque when the load is introduced, and the following error also increases slightly, but the robot stabilizes after 5 seconds.
Okay, finally, for conclusion, the obtained force factor of safety, which indicates a safety against failure, is over 1.3 for the proposed mechanical structure. After this, the structural simulation workflow can be applied to the robotic system based on exoskeleton in order to validate their minimum requirements.
The results of the image processing with the kinetic for Xbox 360 allow to model the desired trajectory in 3 dimensions effectively, and the post-processing done in MATLAB for ENF therapy was optimal for the control process due to the similarities of the capture and simulated motion. A sliding mode controller was designed for the exoskeleton for trajectory tracking tasks, and according to the error values shown in figure 5 and 6, there is a small variation between both tests, which shows the robustness of the SMC algorithm, so it is adaptable to different arm weights. According to the obtained results, the required torque to complete the task without load was less than 20 Newton per meter, but there was a small increase with load, and to move the first and third articulations, the highest torque values are needed. In future works, the controller will be implemented using a digital signal processor to verify its performance.
Thank you very much for your attention. See you.